Welcome to my channel, The Discovery Desk.
Over a narrow 2-month window, India's Defense Research and Development Organization executed a sequence of weapons tests that defies standard operational pacing. We are looking at successful trials across long-range land attack, anti-ship warfare, ballistic missile defense, and hypersonic propulsion. The raw data includes maiden flights of air-launched missiles, full-scale scramjet combustor tests, and trials for armored platforms. For most regional powers, testing a single strategic deterrence platform is a multi-year effort that consumes the bulk of their defense budget and engineering bandwidth. India is advancing hypersonic flight, autonomous armored warfare, and multi-layered missile defense at the exact same time. Very few nations possess the technological depth required to push this many high-end programs in parallel. To understand the scope of this development, we have to map these raw test results onto a systems engineering matrix. This allows us to categorize the recent hardware breakthroughs into 3 distinct interconnected layers: strategic, tactical, and defensive. This framework suggests a shift in focus, away from the procurement of isolated platforms and toward the engineering of a synchronized, multi-domain system. Activating the strategic node brings us to the recent user trial of the advanced Agni platform, conducted by the Strategic Forces Command. This launch tested a major operational upgrade for the Agni lineage. Older iterations of ballistic missiles rely on a unitary payload, delivering a single warhead to a single coordinate. This trial validated the integration of multiple independently targetable re-entry vehicles, or MIRV technology. After launch, the main missile bus exits the Earth's atmosphere. In the exosphere, the BESS sequentially releases individual warheads. Each vehicle plots a unique, independent ballistic trajectory toward a separate geographic target. A single Agni launch can now engage several distinct military installations simultaneously. This MIRV integration exponentially increases strike density. A regional anti-ballistic missile screen designed to intercept a single incoming warhead is mathematically overwhelmed by a single MIRV-equipped launch. Shifting to the tactical strike mode reveals advances in non-ballistic trajectories, led by the long-range land attack cruise missile, often referred to as the Ghost. Tested off Odisha, MISS system projects a 1,500-kilometer radius. The LRLCAM utilizes terrain masking, locking onto an ultra-low altitude path. This topography physically limits the radar horizon of defensive arrays. Furthermore, guidance software executes a zigzag pattern, actively bypassing interception vectors. While the LRLCAM relies on low-altitude evasion, India's upgraded BrahMos cruise missile relies on sheer kinematic force. Recent trials have also pushed the performance envelope of the BrahMos mobile platform. Engineering upgrades to its propulsion and fuel systems have extended its sustained supersonic cruise range. Previously capped at 450 kilometers, the system is now capable of striking targets at Mach 2.8 at distances up to 800 kilometers. Pairing the LRAR-LCAM's radar-evading terrain masking with the BrahMos's supersonic speed provides military planners with extreme regional depth for precision engagement. Drilling down to frontline battlefield systems, we find the Garudastra. This is India's heaviest indigenous 120mm vehicle-mounted mortar. Motorized infantry rely on an operational doctrine called shoot and scoot to survive in contested environments. By integrating GPS and laser guidance, the Garudastra can rapidly acquire a target, fire its payload, and physically relocate before enemy counter-battery radar can calculate its original firing origin. This focus on tactical mobility extends to the air domain with the Terra Glide Bomb Kit, which stands for Tactical Advanced Range Augmentation. The Terra Kit optimizes the cost-to-capability ratio by retrofitting existing stockpiles of unguided bombs with precision guidance hardware. The attached wing kit creates an aerodynamic glide slope, extending standoff range. This allows the launching aircraft to release its payload and turn back, avoiding short-range enemy air defenses. These modular augmentations prove the defense sector is focused on economical, highly scalable upgrades that immediately multiply the effectiveness of units already deployed on the front lines. Activating the final defensive node brings us to the architecture protecting these offensive assets, specifically the 81 and 82 ballistic missile interceptor tests. Protecting launch infrastructure against varied threat profiles requires a multi-layered defense shield. The system uses dual engagement zones with different interception mechanics depending on altitude. One tier destroys threats outside the Earth's atmosphere, while a second handles endo-atmospheric interception. Engaging hypersonic targets requires millisecond tracking software to calculate interception vectors and adjust flight paths in real time. Orchestrating these complex interception parameters is the primary function of specialized hubs like the Integrated Test Range. Offensive strike capabilities are only as resilient as the infrastructure supporting them. By securing that infrastructure, this multi-layered interceptor shield ensures that India's long-range assets remain a viable strategic tool, even under fire. The industrial catalyst driving this 2-month testing anomaly is found in domestic manufacturing policies, specifically the Made in India initiative. The defense sector is executing a strategy of vertical integration. By manufacturing critical subcomponents domestically, the supply chain is no longer bottlenecked by foreign suppliers. Foreign procurement forces a lengthy cycle of import, integration, and eventual upgrade. Localizing the supply chain compresses this into a rapid iteration cycle of immediate prototyping and concurrent trials. This bandwidth enables parallel test tracks, running scramjet trials simultaneously with next-generation armored platform rollouts. The result is a high density of indigenous hardware ready for deployment. When we look back at the systems engineering matrix, fully populated with the Agni MIRV, the LRL-ACM, the AD interceptors, and Tara glide kits, the larger picture becomes clear. Ultimately, the strategic weight of India's modern arsenal lies in the institutional bandwidth required to engineer, iterate, and deploy across the entire spectrum of modern warfare simultaneously.